Today's lesson is going to be on vectors. What we're looking to do in this lesson is to understand that a vector has both magnitude and direction. We'll also be looking at the two different formats for vectors. Okay, we have a component format and a magnitude angle format, and we'll have to convert between those two formats. We'll also add vectors both graphically and mathematically, and the other operations we'll be doing are subtracting them and then multiplying a vector by a scalar. In physics, a lot of times, a simple number is insufficient to describe a value. A lot of times we also need to describe in what direction is a person moving, in what direction is this force being applied. That's where vectors come in. Vectors are simply a mathematical tool that includes both magnitude, which is the length or the size of the vector, as well as the direction. So that's where the importance of vectors. Vectors are going to be very important, so we really need to focus in this unit. Okay, a vector has both magnitude and direction. The magnitude of the vector is basically the length of the vector, or how big is this number, how big is this vector. The direction is usually measured from 0 degrees, okay, where 0 degrees is east, and then we go counterclockwise, making 90 degrees at north, 180 at west, and 270 degrees at south. That's the standard nomenclature that we use. It's okay to use a different nomenclature, but then you have to be very specific, and we'll talk about that in a later lesson. Now, a scalar, however, is similar to a vector. A scalar is the numbers that we've been using all this time in our various classes. Okay, a scalar is just a normal number. It only has a magnitude. The direction doesn't mean anything. Okay, for instance, your weight, actually your mass in kilograms, really doesn't go anywhere. It just sits there. So there's no point in putting a direction on there. When we draw vectors, we try to draw them to scale. What I mean by that is that if I want a bigger vector, a vector with a larger number associated with it, then I need to draw a longer arrow. Okay, we generally use arrows to indicate vectors. In this diagram, I have one vector that's 5 meters per second to the right. It's only 1 centimeter in length. Okay, to draw it to scale, if I wanted a 20 meters per second vector to the right, I would have to draw one that's 4 times longer. Or in the other case, 20 meters per second to the left. Notice it points to the left, and that direction in the arrow direction is going to be used throughout our class. The magnitude of a vector is generally positive. Okay, so because it measures the length or the size of your vector. It doesn't make much sense to say that, I am a negative 1.4 meters tall. Okay, but if I mention something like that, you would probably understand that to me, I'm 1.4 meters tall, I just measured downwards for some odd reason. And that's what it is with negative vectors, okay? It just means that the given direction, if I say 20 meters per second to the right, okay, and if I said minus 20 meters per second to the right, it sounds odd because it is, and what I really mean is that it's a 20 meters per second, but in the opposite direction to the one given, okay, in this case, to the left. Besides drawing arrows to represent vectors, a common format that we write them in is the component format. What I'm looking for in the component format is how long is this vector in the x direction? How long is this vector in the y direction? Okay, so in this example, I have a vector that goes into the northwest direction or in the second quadrant. And if I wrote it in the standard format of magnitude angle, I would have to describe it as 4.24 units. I haven't defined what that unit is, so let's just call it a unit. But it's 4.24 units at 135 degrees. I could also describe it as 45 degrees north of west. Okay, so if I'm going to describe it as north of west, okay, this is the angle I'm talking about, okay, because it's north of the west axis, okay. So I could also describe it that way if I was going to be more specific, okay. So in component format, how far has it moved in the x direction? It hasn't moved in the positive x direction. It's moved minus 3 units in the x direction. So here's my minus 3 units. Okay, and I've also moved positive 3 units in the x direction. So I would describe this in component format as minus 3 I hat plus 3 j hat. What is this I hat j hat? It's just a vector way of representing the x-axis and the y-axis. And we use I hat and j hat primarily because we use the variables x and y as variables, and we don't want to confuse ourselves. I believe IB math represents it in a ordered pair type of format. Okay, if you look at it, it's minus 3, 3. Okay, so if I draw a point at minus 3, 3, like it was for an ordered pair, the vector is from the origin to that dot. Okay, so to convert from that magnitude angle format, okay, how far is it in what direction? That actually requires a little bit of trigonometry. As we go through the year, we'll get a little more fluent with our trigonometry. Hopefully you are already. But in general, we're going to be using sines and cosines to figure out what angle we're talking about. In general, we measure the angle to the horizontal. In this case, the angle to the horizontal is the 0. Okay, and if I look at it, remember the cosine of an angle, okay, the cosine of an angle is equal to the adjacent side over the hypotenuse, okay? So adjacent side in this case is the x-axis. Here's the angle, and here's the x-axis. That's the adjacent side. So the cosine of the angle would be x over whatever the hypotenuse is. And the hypotenuse, remember, is the magnitude. So here's my magnitude of 5, and here's the angle of 37. Doing a little bit of algebra from the cosine formula, I end up with that my x component, okay, this is the x component, the one that would go in front of the I hat, okay, is going to equal 5 times the cosine of 37, or in this case, 4, and let's write the I hat in there. The y component is the opposite side to the angle. So if I want to think opposite side, I have to think the sine of the angle. So in this case, the sine of 37 is equal to the y component over the hypotenuse. Okay, so doing a little bit of algebra, I have the y component is equal to 5 times the sine of 37. Or in this case, 3 j hat. So that's my y component, or the j hat component. Okay. I don't want you to memorize the formulas for the x component or the y component because it varies by which angle you are given. If you are given this angle, the sines and the cosines flip. I want you to remember and apply what you know about trigonometry. Cosine is the adjacent side over the hypotenuse. Tangent is opposite over adjacent, okay? So this is where that SOHCAHTOA mnemonic is going to come in handy. Pay attention to what angle is being given or requested from you. So in component format, here's the vector that we just saw, okay? A, and notice it has a little arrow on top. Okay, there's our little arrow, okay? That little arrow means that what we're looking at is a vector. And in this case, a vector is equal to 4 I hat plus 3 j hat. If I wanted to convert from the component format to the magnitude angle, okay, well, the magnitude, remember, is just the hypotenuse, so we break out the Pythagorean theorem, or the distance formula, and we end up with the square root of the x component squared plus the y component squared, and that's going to equal, in this case, 5. The angle is equal to the inverse tangent of opposite over adjacent, or y over x. In this case, it's 37 degrees. If you're more comfortable using this inverse sine and the inverse cosine, that's okay, but you're going to need to calculate that hypotenuse first if you don't already have it. So we're going to be doing math, okay? Remember, vectors are a mathematical tool, and we're going to be doing some basic algebra with vectors, so where you have to be able to add two vectors, subtract two vectors, or multiply a vector, in our case by a scalar. So we're going to be looking at two different ways that we're going to be adding vectors. We can add them as the arrows that we saw, or we can add them in components. We really can't add them as in the magnitude angle format. So we're not going to look at that one, but let's look at graphically first. When I add vectors graphically, I need to put the tail of one vector at the tip. They have to follow one after another. I start with A, and now I add B. What I mean by adding B is that the tail of B, okay, this is the tail, and that needs to be placed at the tip of A. Okay, so here's the tip of A, and so I need to butt the two vectors together, just like shown. Okay, and this is called tip to tail. Okay, this is the tip to tail method of adding vectors. Okay, the result of that, okay, or the C vector, starts from the beginning of A to the end of B, and this is called the resultant. Okay, C is called the resultant, and remember, it starts from wherever I started to wherever I end. If I think of these vectors as kind of like instructions, go 2 blocks north, turn right, then go 1 block west, okay, and then the resultant is from where you started to where you ended, okay, and if I'm following those instructions, okay, I start the second set of instructions where the first set of directions ended. When I add vectors by component, okay, it's almost like a system of equations. I write the two vectors on top of each other. Okay, so if A vector is 4I hat plus 3j hat, and B is 2I hat minus 2j hat, I just add them up vertically. I add my x's, I add my y's. Okay, so all I really do is add the columns. So my resultant, or C, is going to be 6, which is 4 plus 2, 6I hat plus 1j hat, and it's 1 because it's plus 3 minus 2. Subtracting vectors is going to be very similar to addition. Okay, the one change that you're going to need to remember is that the second vector must be flipped. The reason I flip it is because A vector minus B vector, mathematically when we do that, we're really adding a vector, but it's adding the negative vector. So they're completely identical to say it's A vector plus negative B vector. Well, what's a negative B vector? Remember, a negative vector is just the same vector, but just the wrong direction, okay, 180 degrees. So if I flip it, okay, I get a new one that goes in the opposite direction, okay, and then my resultant is still from where I start to where I finish, okay. So component-wise, it's the same as we do algebraically. It's the top minus the bottom. So 4 minus 2 gives me the resultant of 2I hat. 3 minus minus 2, okay, it becomes the same as 3 plus 2, or 5j hat. So subtracting vectors by component is the same thing we would do as we would do mathematically. The last function that we're going to do is what happens when I multiply it just by a number, okay, multiplying it by a scalar. Okay, multiplying it by a scalar just results in a longer scalar. It doesn't change my direction. Okay, if I look at the angle for 4I hat plus 3j hat, it's the same, okay, as 8I hat plus 6j hat. Okay, I don't change the direction when I multiply it by a scalar, but it does get longer as long as it's not a small fraction. Okay, if it is, then it gets shorter. Okay, so the magnitude just gets multiplied by the scalar, direction does not change. If I look at it from a component standpoint, I'm just distributing that scalar across the components. Okay, thank you.